Okay, so your new textbook breaks this actually into two pieces, whereas your old textbook has it into one piece. So what I'm going to do is I'm going to teach it as two separate lessons, but do it all at once. That way you can learn all this stuff at once and look at all the examples. It is the same overall principle. And then you can use both permutations and combinations as you work your way through your textbook work. So you'll have 2 days in order to do this work. So you can stretch it over a little bit and take your time, get used to it, and so on. Okay. Also, you can use the resources in our online textbook. There's a link in resources as far as how to access our online textbook, and I have given you suggested homework questions from our new textbook, which is online. So if you want to access that instead and try those problems, that's fine too. I'll take up problems from either, so it doesn't make a difference. Okay, so have a peek at that and make a decision based on that as well. Okay, so first we'll start with probability problems involving permutations. Okay, and then we'll work on probability problems involving combinations. Okay, so to start with for permutations, try to remember that permutations are going to be situations where we have positions that are available where someone is given a label that makes them different than someone else. So they're not collections or groups like combinations are, where everybody is kind of treated the same. They're more like situations that involve, you know, positioning or labels. So if I get a group of three, there's a group of three, and that's just three people. But if I get a group of three and I give them, you know, first place, second place, third place, there's three different arrangements in which, or sorry, six different arrangements in which those three people can find themselves. So that's where we need to use permutations. Okay, so anyway, so we see this situation here. So probability, again, remember, is a number of ways in which something can happen over the number of ways in total. Okay, for permutations, it's really going to look like this. This fancy one on the top here, I won't talk about that yet, but the bottom is NPR. Those are all the possibilities. That's usually a simpler permutations type question. NS, remember, is all possibilities that can happen. So if you have 8 people lining up for a photo, then it's going to be 8p8 or 8 factorial. But if you have specific people that have to be in specific positions, like the question that we took up from our last lesson, then you're going to find yourself having a more specific instance. So X, of course, are the specifics that relate to the specific situation that you're dealing with, and A, of course, would be the number of individuals that can go. So if we have NPR, we would take away a certain number of elements for some idea, and then for instead of the R, it's R minus A. We would take away the elements that wouldn't be selected for that particular process or be used in that particular fashion. Okay, so usually, or always, the top is less than the bottom, of course, because we can't have more than 100% probability, or this representation of permutations is going to be a subset of the NPR situation. It's a lot easier. So my recommendation almost always in these questions is to start with NS. Figure out that as if it's its own separate problem. That'll kind of get you warmed up, and then you can do the specifics, the specific conditions and scenarios that make it a success that you're looking for a probability, so that we can do the numerator, okay, which is NA. All right, so here's an example, okay? Mr. Henley's 2-year-old nephew is playing on the fridge with his letter magnets. He has all of the letters that could potentially spell the word phone, assuming he uses all the letters. Okay, so he's got phone, so 5 elements. He's using all the letters, so 5 positions, because of course when you're building a word, where you put the letters makes a difference relative to one another. And we're assuming it's in sort of a linear fashion. So what is the probability that he places these letters in the correct order to spell the word phone? So first thing you go to is NS, almost always NS. I've got 5 elements and 5 positions. How many different ways could you arrange these letters on the fridge or whatever it may be? In this case, you could put 5 elements in the first spot, 4 elements in the second spot, 3 in the third, 2 in the second, 1 in the last, or 5 factorial, or 5p5, whatever you prefer. Okay, and so that's going to be the denominator. That's got us warmed up. We know we're dealing with positions and so on. Now we have to look at, well, what are the specifics? Well, in this case, really, we can only have 1 letter in the first spot, 1 letter in the second spot, 1 letter in the third spot, 1 letter in the fourth spot, 1 letter in the last spot for you to actually spell the word phone. So what it means is there's only one way, or 1 times 1 times 1 times 1 times 1. And so as a result, it ends up being 1 over 5 factorial. Certainly, we didn't really do any specific conditions, but at least it's got us warmed up with permutations, as well as the whole idea of doing NS first is always advisable. Okay, so let's look at a more complicated question. What is the same situation? What is the probability that he places the P and the H side by side. Okay, and hopefully you remember doing these types of questions when we were doing our permutations and combinations unit. But either way, this is where we have to exercise this idea. So first we start with NS in green here. 5 elements, 5 positions, 1, 2, 3, 4, 5 spots, 5, 4, 3, 2, 1, or 5 factorial. That's the denominator. Then we go to the specifics. What we do, remember, is we want to have P and H side by side. Remember, we glue them together as one letter. So we take 2 letters or 2 positions and glue them together as one, kind of like the P and the H or piggyback, or they're one, 3-legged race person stuck together, the P and the H. And then we treat it as if it's its own element, the PH letter. So there's an O, there's an N, there's an E, but there's a PH letter that's stuck together. So now we have 4 elements in 4 positions. Okay, so it's 4 factorial, and then you remember that we can have the P and the H, or the H and the P. They're still together, whatever the order may be. So you take that and you go, well, there's 2 elements. They can arrange in 2 little positions side by side, so that can be the 2 factorial. So that's where we get our numerator. We get 4 factorial, and then we times it by 2 factorial for the PH and the HP arrangement. So 2 elements arranging in 2 positions. Do a little bit of arithmetic, we get a 48. Okay, so then we get a 48 for the pink. For the green, we get a 120. That's what 5 factorial is. And 48 out of 120 is 2/5, or we reduce it at 0.4000. Again, 4 decimal places always for probability. Okay, we move on to another permutations example. 12 finely tuned athletes in Berkozzi's phys ed class are getting ready to run the 100-meter dash. Okay, so they're lined up on the track, they're getting ready to go. Assume they all finish. Okay, no one gets injured or something along the way. What is the probability that they will finish in order of ascending age? Ascending age means they go from, I guess, first place would be the youngest, and then last place would be the oldest. Or I guess it could be the other way around, but we'll pick one of those. Either way, it's in a very specific order. So what do we do? Well, we've got 12 finely tuned athletes. Oops, I did this as if it was 10. So there should be 12 factorial. Okay, 12 elements, 12 positions, 12 factorial. Sorry about that. Okay, so that's my NS. Okay, 12 people in 12 positions. For this scenario here, for my ascending, well, there's only one way they could go in their actual particular age. I mean, no one probably has exactly the same age when you bring it down to the nearest second. They may have the same birthday, but not the same second, the same minute, the same hour of the same day. And if they do, that's amazing. But I guess it's possible. But either way, we assume not. So there's only one way to do that. So it's 1 over, again, that should be 12 factorial, which is a little bit larger of a number. So it'll be 1 over 12. There's a factorial on this one. Ah, there it is. It's my daughter's calculator. Okay, so a little bit bigger of a number, 479 million. Okay, so a little bit less probable. Okay, in that case, actually writing it as a fraction is a little bit better, because if you write it as a decimal to 4 decimal places, it's going to look like nothing, 0.0000. Okay, it's going to look like it's impossible. Okay, so oops, sorry about that. Maybe correct your notes. Okay, anyway, we'll move on. All right, what is the probability that Julia, Corina, and Farah finish first, second, and third, respectively? So here I go on with the same theme of 10 factorial. That's my boo-boo. It should be 12 factorial because we have 12 athletes. Okay, so that should be a 12. But either way, what I do is I start with my NS. Okay, 12 elements and 12 positions should be 12 factorial. And then what I do is I go ahead and then I do the specifics. That's the green one that I have here. Again, it should be 12 elements and 12 positions. But what I've done is I've placed Julia first, respectively means Julia's first, Corina's second, and Farah's third. So Julia, Corina, Farah, that's the JKF. I fix those positions, and then I have the rest of the elements afterwards. And this, of course, is my example if I had 10 elements where I made the boo-boo, and so the result is 7 factorial, 1 times 1 times 1, and then 7 people left over. But if you do it correctly for the 12 people, then it would be 1, 1, 1, and then it would go 9, 8, 7, 6, 5, 4, 3, 2, 1, and so it would be 9 factorial. So the proper answer should be 9 factorial over 12 factorial. But instead, because I thought there was 10 elements, silly me, it's 7 factorial over 10 factorial, which then reduces down to 1 over 720. Okay, 9 factorial over 12 factorial would be a little bit less of a number. Okay, so it would reduce down, but certainly not to the nearest degree. It would be 1 over 12 times 11 times 10. 11 times 10 is 110. 12 times that is 1100 plus two more of those, which is 220, so it'd be 1320. So it'd be 1 over 1320. But either way, sorry about the boo-boo. Again, I make the same boo-boo in this question too. Maybe I should have just changed this to 10. That would have made my life a little easier. But either way, I guess I should go along and correct this afterwards. But what is the probability that these 3 ladies will finish in the top 3? It's a little bit more interesting. Okay, rather than finishing first, second, third in those particular orders, it's in the top 3. So I orient that a little bit different. Again, I do the same thing. I'm assuming 10 elements in 10 positions, even though there's 12 people. Okay, so there should be 12 factorial. And then for the bottom part, or for the numerator, okay, the green, what I do is I take my top 3 positions. Okay, and really I have 3 elements in 3 positions, or 3 factorial. Okay, because those ladies could finish in any particular order. Okay, and if you wrote them all out, there would be 6 possibilities. Or there would be 3 ladies who could finish first, 2 ladies who would finish second because one is finishing first, and then 1 lady left to finish third because the other 2 had been placed in that position. And then the remainder, of course, would be the remainder of elements factorial. In this case, I pretend that there's 10, or I made the mistake that there's 10. So these 3 would be oriented as 3 factorial, and then we go 7, 6, 5, 4, 3, 2, 1. But of course, if there was 12, these 3 would still be oriented this way, and it would go 9, 8, 7, 6, 5, 4, 3, 2, 1. So a few more spaces, and then of course I'd evaluate from there. You'd end up with a numerator of 6, and then a denominator of 9 over 12. It'd be the same same denominator here, which was 1320. So you'd end up with 6 out of 1320. That of course would reduce down to 3 out of 660. Oops, no, that would be 1 out of 220. But either way, you go ahead and you figure it out. Sorry about the boo-boo for that one. That's a little embarrassing, but that's okay. Okay, it's a process that we go through. Okay, so if you really want all of these notes to work out, then take that number 12, scratch it out and put a 10, and all of these answers are beautiful. Okay, so maybe that's a better way for you to go over these notes, is to fix that one. Sorry about that. A few more examples. Okay, a few more examples. Our Loyola graduating class is 263 students with 133 males and 130 females. If students need to vote for valedictorian, salutatorian, and student of the year, or any particular fashion, again, I'm choosing a group of 3 from this large amount of males and females, or whatever it may be. However, we do have this situation where they each have a position once they're chosen. So it's not a combination, it's a permutation. Okay, so I know I'm dealing with permutations. Again, I start with NS, 263 elements. Anybody could be any of those 3. So it's going to be 263 P3. Okay, remembering, of course, that they're different from one another. They're not a group of 3 top students. They are the valedictorian, salutatorian, and the student of the year. So there we have our 263 P3. That's our bottom. No real considerations. Now we look at the actual part of the question. What is the probability that all 3 honors go to females? And then the second question is males. So there's actually 2 separate questions in this question. Okay, so we look at the number of ways in which we can get all males. Okay, well, that means that we don't have 263 elements to choose from. We have 133 elements to choose from because there's 133 males. So it's going to be 133 P3. No other conditions are placed on there. So 133 P3. Okay, all over, of course, the 263 P3. So that's the probability that they're all males. For females, right underneath the females word, same idea. We're going to have 130 females, so it'll be 130 P3. Okay, or 3 elements taken from 130 and placed into a position. And then, of course, this is the same 263 P3 in this situation. Okay, so again, you get yourself warmed up with your NS, and then you go straight for your NA. Okay, second example, what is the probability that the valedictorian is male, but the other 2 go to females? Okay, that's a little bit more specific. Again, denominator NS, 263 elements, 3 people are chosen, different positions, so 263 P3. But the numerator is a little bit different. What I actually have to do is to do 2 sets of choosing. And you can outline this by doing spaces if you want to. It's just a little bit daunting with the numbers. They're pretty big. But either way, for me to choose the male valedictorian, that's the valedictorian, 133 P1. For me to choose the female valedictorian, it's going to be 130 P2. Now, it's 1 and then those other 2, so we're going to multiply them as well, and it's fairly specific and prescriptive. Okay, so when we do those calculations, all the way banging out the numbers here, we end up in, again, a probability for decimal places. That's the standard way in which we do it. If you don't feel like reducing, that's a surefire way to get full form marks, all right, is to go ahead and just turn it into a decimal, 4 decimal places, and I put approximately equal to it. Put a little dot over top of there to represent approximately equal to, and don't forget your closing statements with your proper P notation. For C, what is the probability that all 3 awards will come from our class? Okay, well, we have to have a size of our class. That's an important feature. It's not really included in this question, so I guess this would be a question that would vary from year to year if I was to use the same notes. So again, we've got the same NS, if we have the same 263 students, so 263 P3, 263 P3. And let's say that we had 27 students in the class. Okay, it'd be 27 elements P3. Again, positions are important because we still have valedictorian, salutatorian, and student of the year. Okay, so that being the case, there is my an A, which is 27, P3, 27 elements to choose from, and I have 3 positions to put them into. There are my values, and then I go ahead, and as you can see, it's a fairly small value for the final result in there. Now I'm going to stop this just because it's permutations, not because this is the stop of the lesson, but for those of you guys who want to break it into 2 pieces, you can go ahead and get on the new textbook homework if you want to. It's either in pink or green. I can't remember what colors I've put it in on your day-by-day plan. The only homework that I have is from the old textbook that's stated in the actual lesson for permutations and combinations. So as a result, our problems involving permutations and combinations. So as a result, if you're going to use the old book, and that's cool, then watch the next video on combinations as well, and then you can dive into things. So press pause.